So we will start again. So Exergy. So my question is, who knows what is the meaning of Exergy? Okay, there are 2 that say yes, 3, 4. So there are some people that knows about Exergy. So I would say, now I will rephrase my question. So who is able to give me the definition of Exergy? Okay, let's go.
The maximum amount of work that can be retrieved at any given state.
Yeah, the one that know the definition of Exergy are happy with this definition? Yes? No? Something missing? No, so go ahead.
It's really hard to describe what Exergy is, but it's energy that is completely usable.
Yeah, okay. So, but what is the difference with what he has said?
Can you repeat your definition?
The process has to be reversible. At a given state, it's the maximum amount of work that can be retrieved.
Yeah, and then you said?
Yeah, so the process has to be reversible to obtain this maximum.
Yeah, that's so reversibility is important, but it is related to the maximum, huh?
Yeah.
Right?
Yeah, it is the same.
And?
I think it's not dependent on the state.
No, it is.
Like you have electricity, which is pure Exergy.
Yeah, but yeah, see.
It's a property of the state.
Yeah, it's a property of a state. So that's correct. Huh? But in reality, something is missing. So the Exergy is the maximum amount of work that can be produced by any state by doing reversible processes, and that's why it's maximum, and by exchanging with the environment only. Okay, so what was missing in your definition is the environment. Okay, so it means that the Exergy of a heat load in Sweden and in South Arabia is not the same, right? Due to the fact that the environment is different, right? And this is true as well on the moon. Huh? So there were some attempts, for example, to build nuclear power plants on the moon because the temperature was much lower, and it was therefore the heat at a certain temperature had a much higher value of the Exergy. Okay, so and the maximum, the definition of maximum is because the system is reversible. Okay, so let's look at how it formulates at the level of the theory. And for this, we have to look at a system. So you are talking about states. I do agree with the state but the state is belonging to a system. Okay, and typically in the system we have exchanges in form of heat, in form of work, and in form of mass flows. Okay, and typically mass flows are involved in what we name a network. So it's an interconnection of flows inside the system. Okay. In this system, what we can do is to write the first law of thermodynamics that is going to tell us that what is entering the system will leave the system. Okay, perhaps not in the same form. Okay, but what is entering has to leave the system. Or accumulate inside the system. And most of the time what we will consider is that we will ignore, at least for the time being, the accumulation, which means that the energy balance will be expressed as being the sum of the work that is entering the system. And just for those who are not used with this terminology, I would like just to give the definition. So a plus here as a subscript is if you see plus, it means that it is positive when it is entering the system. Okay. When I will use a minus as a subscript, it will mean that the value will be positive when it leaves the system. Okay. So what I'm saying here is that the sum of the work plus the sum of the heat and plus the sum of the energy value of the mass flows is equal to 0. And of course, there will be something that is going to leave and something that is going to enter, which to enter, which means that there will be positive and negative flows. So it means that if the heat is leaving, it will have a minus sign here because it is accounted as positive when it enters, right? So it's a trick to be more general. So when we look at the mass, we have to be able to characterize the energy content of a mass flow, and we typically consider there are 3 types of energy that is associated to the mass flow. The one that is related to its state, so it's the energy content of the state, which comes from the temperature and the pressure mainly. The kinetic energy that is related to the speed, and the potential energy that is related to the gravity and that is related to the height at which the mass is available. So this is mainly what we will use in the hydropower plants. This is what we will use in the turbines, for example, and this is what we will use for the heat exchange. So characterizing a state is typically done by characterizing the enthalpy, and the enthalpy is calculated this way. The enthalpy at the temperature and pressure is equal to the enthalpy of formation, so it's the amount of energy that is embedded into the molecules that we will use for the combustion, for example, plus a contribution that is a sensible heat, which is related to the Cp here. At the same time, I can also write the entropy content. And the entropy content is coming from, so the definition of the entropy is coming from the ratio between the heat load and the temperatures. And the entropy is related to this ratio. And the entropy at the given temperature and pressure is calculated as being the entropy of formation, so it's the entropy that is embedded into the molecule, plus a contribution that is Cp over T times the temperature variations, minus something which is coming from the pressure, which is R ln of the ratio between the pressure and a reference pressure. Something which is important here is that the calculation of the entropy is always taken as a function of a reference, okay, which has to be the same for all the flows that you consider, otherwise it will be very difficult to make comparisons, okay? But don't forget that this reference is always there, even if we simplify or oversimplify, the reference is always there, and it's selected arbitrarily. As I'm a chemical engineer, the reference is, for example, the gas state at 1 bar and 25 degrees C, okay, which might not exist in reality, but it will be my reference for making all the calculations. So when we have a flow which is composed of more than one compound, then what we have to do is to make the sum of the contribution of each of the compounds. So it means that the enthalpy of a mixture is the weighted sum of each of the compounds in the mixture, the weighted sum of the enthalpy of each of the compounds of the mixture. And each one has another Cp, so it means that this one is specific to each of the compounds. Okay. And when we mix, when we mix streams to calculate the entropy, then we have to add something which is the contributions of the mixing, which is coming from the entropy created by the fact that each stream has a certain concentration. So we can express this as being the energy that would be needed to separate them as separate compounds. Okay, so this is the entropy. When we have this, we can apply two different very important principles. The first one is that the energy is conserved, okay, as the mass is conserved. So it means that I cannot create energy, I cannot produce energy. So it means that all the people who are mainly people from the electrical engineering. Are there people from electrical engineering here? No. So in electrical engineering, they have the temptation to say that they are producing energy. Okay, energy cannot be produced. Okay, impossible. Electricity can be produced out of another form of energy. This I have no problem. But the energy cannot be produced. Okay, this is what the first principle is telling us, which is expressed by this equation here. So it means that the work plus the heat plus the mass flows, the energy content of the mass flows is equal to 0 if there is no accumulation. And then there is a second principle of thermodynamics that tells us that the entropy creation is always of an isolated system is always increasing, which is expressed by this expression here. So those are the contributions of entropy of the heat. The work is a pure form of exergy, so it means that it has no entropy content. Okay, and then you have the contributions coming from the mass flows, which are associated to the entropy content of each of the mass flows. So now what I can do is to take the two principles and combine them. So this one is expressed in form of energy. Okay, so it's in this case is kilowatt. The entropy variation is expressed in kilowatt per degree K. Okay, you can see here. But it means that if I'm multiplying this this equation here by a reference temperature, which is the temperature of the environment, then I have two equations, this one and this one, that have the same unit, so I can make the sum of the two. Okay? So if I can make the sum, I can also make the difference. So what I'm going to do now is making the difference between the first principle, which is the energy balance, and the second principle is multiplied by the TA here, which is then creating this equation here. And this equation here, as I have made a minus here, is telling me that the contribution of the work plus the contribution of the heat load multiplied by this factor here, which is the Carnot factor, plus the enthalpy contributions minus the TA times the entropy contributions, and this term here is what we name the co-enthalpy, has to be bigger or equal to 0. Lower, equal to 0. Okay? Which means that I can calculate, and pay attention that I have made a small astuce here. I changed the plus into minus here, which is going to tell me that the maximum, the amount of work that is extracted out of the system is always lower than the contribution of the heat and the contributions here of the mass flows expressed by what we name the co-enthalpies, right? So if the amount of work is always lower than this value, it means that the maximum amount of work that I can produce out of in this system is equal to the contribution of the heat and the contribution of the mass flows expressed by what we name the co-enthalpies. I'm able, therefore, to define, with a given set of processes, the maximum amount of work that can be produced. And you can see that you have here the ambient conditions that are used as a reference, okay? And you can see as well that the maximum here holds if this expression here is equal to 0, right? Which means that the processes are reversible because they are not going to create entropy. Okay? So then we go back to what you were saying. So the maximum amount of work that can be produced from any state or any system that goes back to the equilibrium to the environment. Right? So I have the maximum amount, so it means that I can also calculate the amount of work that I will never be allowed to produce anymore if I'm realizing the system as it is observed here. Okay? You can see that the difference between the maximum amount that I have calculated and the one that I'm doing effectively is what we name the Exergy loss. And it is lost, okay? And nobody can recover it anymore. It's too late. Okay? And it is the amount of work that will never be produced anymore because I have realized the conversion in the system that is here. Okay? And this system is satisfying the energy balance. So it is satisfying the equation here. So it means that everything is well settled, but I have lost the capability of producing a certain amount of work. Okay? So this is really important for you engineers. Okay? Because it means that if you have any device or any system that is converting energy, it is following the first principle of thermodynamics, you can calculate how much the amount of work that you will never be able anymore to produce, okay? And the better you will be, the lower this value will be. Okay? And it's important to realize that when I'm writing this equation, in fact, the work is Exergy. There is an equivalent Exergy value of the heat, which is expressed using the Carnot factor, and the Carnot factor is expressed, so we are talking about thermodynamics. When we speak about thermodynamics, temperatures are in Kelvin, right? Okay? Always. So you have here the Carnot factor that is applied to the heat that is considered with the temperature at which the heat is available, which defines what is named the heat exergy. And then you have here the amount of the value of the exergetic value of each of the mass flows in the system, which then afterwards relates to the Exergy loss, which is the temperature multiplied by the variation of the entropy. So the simplification of this expression is here. Now, if I want to give, to express what is the Exergy content of a fluid that is going to be cooled down. So it means, let's assume that I have a fluid that is at the given inlet temperature here, and that is going to be cooled down to the outlet conditions here. Okay. In fact, I can define this in two different ways. Yeah?
But just for the notation, the plus and the minus, what does it mean? It's the input and output, or
the plus is indicating that with respect to my system, when the flow is entering to my system, if it has a plus, it means that the value will be positive. Okay? And my problem is that it is with respect to the system that I have selected. So it depends, and I will show you an example here. So the heat, in this case, I will define the heat that I receive. Okay? And for my system, I will receive heat, so it will be counted as positive when entering into the system. And I'm going to produce electricity, and I'm therefore going to use the minus to declare the electricity that is produced will be positive if it leaves the system. Okay? So it's just in my head to have highlight the flow direction. Okay? And it simplifies the complexity of the equations. Otherwise, I would have always to write the sum of the inlets minus the sum of the outlets. Okay? So, if I'm looking at this fluid that is going to be cooled down, in fact, I can calculate the amount of work that can be produced by considering that when the fluid is at this temperature here, if it delivers a small amount of heat, okay, and it will be at a given temperature, at Tin, okay, which means that I can calculate how much electricity or how much work it can produce by using this formula here. So it means a very small amount of heat at the temperature, which is the mean temperature here, okay. And then what is going to happen is that the temperature is going to decrease. So it means that the next one will be at a lower temperature, etc. And so, therefore, if I want to do the calculation of the total amount of heat that is delivered from this temperature to this one, okay, I will have to make the integral from T in to T out, okay, which will define the maximum amount of work that can be produced. I know as well that the maximum amount is expressed by the fact that I have a flow that is at T in here that will enter a device here and then will end up with in another state here. So the maximum amount is also the flow times the this term here, which is named the co-enthalpy. So the co-enthalpy is the enthalpy minus TA times the entropy. Okay. So it means that the maximum amount is also the flow times the difference of co-enthalpy, which is expressed here by the enthalpy minus TAS. And I have here the way to calculate the enthalpy and the entropy. Okay. Now if I'm replacing then the definition here and here in this expression here, I will have this expression here. Okay, which is going to tell me that the maximum amount of work that they can produce is equal to the flow times the CP multiplied by 1 minus the ratio between the ambient temperature and the temperature of the source, and it's an integral over the variation of the temperature. So if I'm taking this expression here now, and if I'm trying to, if I'm considering that the CP is a constant, okay, which is valid if I do not have a big temperature difference, right? Then I will end up with this expression here, because now I can do the integral in a very easy way, and I'm obtaining the MCP times the temperature difference minus TA times the logarithm. The logarithm is coming from the integral of the 1 over t here, multiplied by TA, which is a constant. So the difference of the logarithm here. Okay. And now if I remember that this amount here is the heat load, and if I'm assuming TLM as being the difference of the logarithmic mean of the temperatures between the inlet and the outlets, okay, I end up with this equation here. So, which is defining that the maximum amount of work that can be produced by the heat load that is delivered by going from T in to T out is equal to the heat load times this kind of factor here, where the temperature is a mean temperature and is the mean the logarithmic mean temperature. Okay? Only valid if the MCP, the CP here is a constant. Okay? But it's interesting because it means that the heat delivered by the enthalpy difference between T in and T out can be expressed as a value of the heat delivered for a given mean temperature, which is the logarithmic mean temperature. Okay? So this allows me to be quite precise in the definition of the amount of work that can be produced when I'm doing a heat exchange. Okay? Now, something that would be nice would be to know what is the amount of effective work that I can produce out of the maximum amount. Because the maximum amount, I know it is a process that has to be infinitively slow, which would require a very, very big area so that it can go back always at any time. Okay, it means that it's not interesting from the engineering point of view. So now what we can say is that I can compare the work that I would produce by cooling this stream and having a very nice machine that is going to really produce a certain amount of electricity here or work here. And what I can tell you is that a priori, there is what we name an efficiency between, that is the ratio between the amount of work that is effectively produced compared to the maximum amount that can be produced. And this ratio is of the order of magnitude of 55%. So this is the order of magnitude of what the engineers are doing today. Okay, you give me a heat load of hot water coming from the ground, and I can convert it into electricity with an efficiency which is the maximum efficiency calculated here, obtained by this Carnot factor here, multiplied by 55. 55, 56, the better you are, or the more sophisticated you are, then the efficiency is going to increase, right? But this is easy to take as a rule of thumb because I do not have to then design the system, okay? So what I'm saying is that I know that someone in my colleagues will be able to design a system that will have this 55% efficiency, which means that I do not have to design the Rankine cycle that is going to convert the heat that I have here. I have already a guess of how much it will deliver. Another thing which is very important with the Exergy is the fact that it is reversible. It means also that I can calculate the amount of work that would be needed in order to heat a flow from an inlet temperature to an outlet temperature. Okay? And this is quite interesting because it would mean that I would install a heat pump in reality, okay? Taking the heat from the ambience and then heating the flow here, right? And I will calculate how much electricity I have to consume. The rest coming from the environment. Okay? And this is also very important because it gives also then the reverse value. So how much do I have to pay to go from this temperature to this one? Okay? For example, how much Exergy do I need or work do I need to heat a house which is at 20 degrees C when the temperature outside is 0? Okay? And it will be very small. Okay? And the 55% works as well for the heat pumps. And in this case, of course, this is the minimum amount of work that is needed. The reality is that I will need more, so I will have to divide by this 55% to have the real amount that will be consumed by the heat pump, the corresponding heat pump. Okay? Which means also that I can then afterwards calculate what are the Exergy losses that occur in a heat exchanger. So in a heat exchanger, I have a hot stream that is cooled down, and I have a cold stream that is heated up. Okay, so now I can say, well, the hot stream that is cooled down can be, would have the possibility of producing a certain amount of work by exchanging with the environment, and this will give me this value here. And this one needs a certain amount of work to be heated, and this will give the value here. And the difference between the two is the amount of work that I could have produced. So I'm producing work here and consuming work for heating the flow here. So the difference between the two is a given amount of work that I could have produced, but that I cannot produce anymore. Okay, so this is the losses that occur inside the heat exchanger. Right? And this is the formula that allows me to calculate what are the heat losses in the Exergy losses, sorry, in a heat exchanger. Okay, and this value is indeed very useful to know if a heat exchanger is well placed or destroys a lot of Exergy because of a big temperature difference between the two. Okay? So do you have questions about this calculation of the Exergy, and especially the one that is related to the heat? The one that is related to the heat is the one that we are going to deal with a lot in this lecture, so it's important to understand it. No questions? Yeah.
1 millisecond ambience divided by T logarithm mean. Isn't it the Carnot efficiency itself? The definition for like.
It's the Carnot factor.
Yeah.
So this is the Carnot factor, huh? This element here.
So to get the actual flux we can add, we just have to do the heat flux times the Carnot factor squared.
Yeah. So this is really what is expressed here. Huh? So this is the heat load delivered multiplied by the Carnot factor, which defines in fact the maximum amount of work that can be produced by cooling this flow from here to here. Right? And then the other one, the other term that is here, is I'm receiving a certain amount of heat to go from this temperature to this one, and it corresponds, it needs a certain amount of work to be produced, to be delivered. And so now what I'm saying here is that, in fact, I can always use the work that is produced here to produce the work that is needed here. Okay? But what is happening here is that in a reversible process, I will produce more work by cooling down those flows that are hotter than heating those ones that are colder. Okay? And the difference between the two is, so the difference in work between the two is the amount of work that I have lost in the system. The system has effectively heated this flow from there to there by cooling down this one from there to there. But unfortunately, by doing this process, I have lost a certain capacity of producing work. Okay, so if I'm extending the concept, what you can see is that if now, let's not right here, I'm doing exactly the same, and I'm using the combustion gases that I'm cooling down, okay, with cold water, okay. In this case, I have lost completely the capacity I have to produce work. Okay, and of course, the people do, what the people do is that they, for example, produce steam out of the out of the combustion gases. Okay, and they cool it down afterwards by exchanging with the cooling water, which is here. and in the meantime, they extract some Exergy out work. Okay, but still, I'm losing some because there is a temperature. There are different temperature differences here and here. Okay, and then if you remember your lectures in Thermo 2, for example, then what we do is that we do 2 stages, for example, just to have less losses there. Okay, and produce more work. Right?
But you said the losses of the max exergy that we can have, and we remove the effective exergy that we really use. And you said the effective one is the kernel factor times the max exergy now. So
say it again.
you said the losses are the max exergy we can have, and we remove the effective exergy we use.
No, which is defined as being the minimum amount of work that is needed to produce to heat. Huh?
Okay.
Okay, so it's on both sides. It's a reversible processes. Okay, so what I'm making as a difference is the amount of work that I could have produced by cooling down the hot spring here, minus the amount that is the minimum amount that is needed to heat up this one. Okay, and the difference between the two is lost because I could have extracted more electricity a priori or work a priori, but by the fact that I have installed this heat exchanger, I cannot do anything else. It's too late. Okay? But it allows us to understand what is happening inside the system. Okay? So, I will perhaps keep this one and go into this one. So I have discussed about the effect of the heat. We can also have the same analysis when you do an expansion. So it means that you can always do a heat exchange with the environment and then an expansion that is then recovering the mechanical work. And again, we will have the same expression here. So you will have a part that is coming from the temperature and a part that is going to come from the pressure, which will translate into another dimension, which introduces the effect of the pressure in addition to the effect of the temperature. So the ln here, which is coming from the integral, is associated to the temperature, and this one is associated to the pressure change, which means that by using the concept of entropy and enthalpy, we have the possibility not only to characterize the exergy or the work potential of streams that do change in temperature, but also the potential of streams that do a change in pressure in a compressor or in a turbine. Okay, and something which is interesting with the exergy related to compressors and turbine is that typically we calculate it with isentropic efficiency, and the isentropic efficiency is in fact related to the maximum amount of work that can be produced if the process is isentropic, so without creation of entropy, which means that the exergy losses of an expansion or of a compression is in fact the difference between the enthalpy, the isentropic enthalpy and the real enthalpy of the system. Okay, is a T times delta S. And then I can also do the same reasoning for combustion, for chemical reactions. Okay. In this case, I will have to account for two different aspects. Because if I'm doing chemical reactions, it means that I have some molecules that are given and are a given state. Okay? And they will, by making the chemical reaction, create new molecules, which will have new states. Okay, so for example, I will have methane, CH4, and I will produce CO2 and water. Okay, so if I want to be able to calculate the enthalpy, the co-enthalpy, so the capacity of producing work of those flows, I will have to look at the composition, and I will have to take into account the enthalpy and the entropy of formation of the different compounds that are concerned. Okay, the one that are in the original state, so the fuel, and the one that are in the target state or the end state, which is the CO2 and the water. And something which will be difficult there is that I will have to decide what is the equilibrium with the environment. Okay, so I need to know, if I want to know what is the quality of a molecule that is emitted. So, for example, I'm going to emit SO2. Is this what is the value of this compound compared to an equilibrium state in the environment? And there, it's not always so clear about what is the best state to consider. So, for example, I have water. Do I consider water in a gas phase in equilibrium with the air that is in the environment? Do I consider liquid state, which is the water which is flowing just nearby? Okay, so I will have to be a little bit careful with this. The other dimension being related to the concentration. So I'm releasing, I have carbon dioxide, which is in my chimney that has been produced by combustion. In fact, this carbon dioxide has a higher partial pressure than the carbon dioxide in the atmosphere. So it means that officially I can expand it from the partial pressure that it has in the chimney to the partial pressure that it has in the environment. Okay, so officially I have also to take into account this diffusion energy that is hidden there. Okay, so which means that for the enthalpy and the entropy of formation, we need to have consensus definition, and I give you one. I'm not sure that it is the only one that can be used, but at least those ones are given by or have been fixed by a list of scientists that defines so the amount of so the co-enthalpy for the different fuel that we have here and the corresponding chemical reaction, which allows us to have then the entropy and the co-enthalpies of any fluid that we are going to manage and to deal with in our lecture. Okay, and so here I'm comparing the heat of reaction, for example, and I will take an example here is the heat of reaction of methane. The heat of reaction of methane, the energy is 50,000. This is the lower heating value, this is the higher heating value, and the Exergy content, so the co-enthalpy is 51, so it is something in between. Okay, and the reason for this is that the higher heating value is going to condense everything, while here the water will remain in the gas phase, partly. Okay. Right, so now I have the way to characterize the heat flows, the mechanical or the physical transformations, and to characterize the flows that I have in the system. So it means that I can make balances that will allow me to assess the efficiency of systems. So for example, what I will do is that I'm going to look at the amount of Exergy that I'm buying in my system. So the amount that enters in form of heat, the amount that is entering in form of work, the amount that is entering with the mass flows that are entering the system at the state where they are. So each entrance is specific, of course, with a given composition. And I will make the sum of all the Exergy that is delivered by the system in form of heat, in form of work, and in form of transformed compounds that are, or flows that are leaving the system, right? And now I can look at the the efficiency of the system by making the ratio between the exergy that is delivered, which is what is the exergy content of the flows leaving the operation, and the exergy that is consumed, which is the exergy that is entering the system. Now, if I'm looking at the balance, what I can see as well is that I can define it as a function of the losses, because the efficiency is also 1 minus the losses divided by the exergy input. Okay? You all agree? I guess that the answer is yes. Right? Okay? So you all agree, but I would like to insist on something. Okay? This is a very nice definition, so it's what is entering minus what is delivered. But here is the definition of what is delivered. So it means that if you release the flow in the environment, even if it has still an exergy, but if you release it in the environment, it is lost, diluted in the environment. So it means that the flow here, so what is delivered has to be carefully defined, because it's possible that here I have also losses. Okay, the same here. So I can have a huge amount of hot water leaving the system, but if nobody is using the water and I'm releasing the water in the sewage, okay, then it's a loss as well. Okay, so we have to be really careful in defining what is useful and what is not. Okay, but on the other hand, having a quantification of the amount that is here will perhaps tell you, oops, I have to pay attention on this value because it has a high value. The same here. So if I'm delivering combustion gases at 200 degrees C, I can still cool it down to 25 degrees C. And I can, by defining this co-enthalpy content, I can define what is the amount of work that I could produce with what is remaining. Okay? So it means that we have to be careful. And then, of course, we have also to look at systems in a broader sense. So it means that we do not look at one unit, but we can have a combination of units. So, for example, here, it's a gas turbine that is entering at with a given amount of fuel here. Pay attention that I'm not entering the air because it is coming from the ambient, so I'm just considering that it is zero from the exergy point of view. And this amount of energy is being converted into work and into heat for heating a fluid from T1 to T2. And there I have to express what is the exergy efficiency of the system. So from the energy balance, it's not so complicated to write. So I have the amount of energy that is produced by the efficiency of the gas turbine, and then the amount of heat that is delivered to heat the flows from T2 to T1, which corresponds to cooling the gas from T3 to T4. Okay, and therefore I can calculate also the amount of energy that I'm losing here by releasing the heat to the environment at T4. The exergy value will give me another definition, because then I will see that, okay, there is a part of, and this is what is named the Sankey diagram, where we try to express what is, to represent what is the share of the different form of exergy. So here I have the total amount that is entering here in form of fuel. Out of this fuel, I have a certain amount that is expressed in terms of exergy as being the electricity that is produced. And there is another part, which is the exergy that is made available in the combustion gases at T3. That could be cooled down to T ambient and gives me a certain amount of exergy that is valuable here. Which means that out of the total amount of exergy that has entered the system, there is a part that is useful in form of work, a part that is useful in form of heat, but there is also a part that is already lost. And this is lost because I have realized a combustion in the gas turbine burner. And I have lost some exergy because my compressor is not 100% isentropic and my turbine nature. Right? So it means that I have lost a certain amount of capacity to produce work anymore by the operations that happens in the gas turbine. Now, I have a certain amount of exergy in the combustion gases, which are expressed here, which is the total amount that can be recovered out of the combustion gases. And now I realize that I'm using this amount to heat a process from T1 to T2, so this is the useful part, okay? And I know that I'm releasing a certain amount from T4 to T ambient in form of waste gases, which is here. And what I can see here is that I'm losing this amount, so the gray part here, in form of exergy that is lost in the heat exchange. Okay, and you can see that this amount is quite big, mainly because T3 to T4, so T3 is 700, T4 is 120, while T1 and T2 is 50 to 90. Okay, very big temperature difference, big losses in the operation. Okay, so and then of course I can represent those transformations and efficiency in different ways. So this is again a Sankey diagram for something which is a little bit similar, except the fact that I have decided to add a new heat exchangers that is producing steam, that is expanded in the turbine, and that is afterwards delivering the heat at a higher temperature here. And in this case, so this is what is happening in terms of energy, and this is what is happening in terms of exergy. Okay, and you can see that every one of the operation has an exergy loss corresponding to something which is not useful. The only thing that is in reality useful in my system is the electricity of the gas turbine, the electricity of the steam turbine, and the useful heat that is sent to the process. All the rest, this part here, is lost in the environment. So in this case, the system has a novel exergy efficiency of 50% more or less, so not far from the 55, but I know that if I would have to increase the efficiency of this system, I would have to increase the temperature of the steam turbine, perhaps use a 2 pressure level to be more efficient in producing more steam, and which would then mean that I would convert part of the part that is lost here and here into more electricity here to satisfy the needs of the process. Okay? Questions about this? No question? So there will be a speak out that will be open for next week, because you will have to do an exergy analysis of the process that you have been asked to evaluate up to now. Okay? So now you have the flows, you have the enthalpy. Most of the operations are related to heat exchange, and so you will be in a position of either plotting some such Sankey diagram, or at least calculating the exergy loss in each of the units that you have in the system and identify which are the ones that are responsible for the major losses. Okay? No questions? Crystal clear? So let's apply them. So we do a 15 minutes break, and then afterwards Francesca is going to perhaps just give some hints on how to deal with the different subsystems that you have in the exercise. Okay? Okay.